All right, welcome. In this video, I want to take a look at another greedy algorithm with a couple counterexamples and also a proof of correctness. And like the last video that we looked at, I want to look at another example of a problem where our argument is going to be a little bit more logical and a little less mathematical. The first couple examples we showed, our argument tended to rely a lot on algebra. That's not always going to be the case. So this is intended to be another example where the algebra is fairly simple or almost straightforward, but the reasoning, the logic, is a little bit more in depth. So to get started, I wanted to present us with a real world problem that we can maybe get a little bit of practice applying our tool of abstraction to build the information processing problem, the input and output criteria that we're going to then try and solve with our algorithm. So to start out here, I'm just going to start with this real world problem. So you, Alice, and Bob are attending a computer science conference at which there are numerous talks, panels, exhibits, other events that you want to attend. They all start and end at different times, and it's impossible for us to attend all of the different events because they overlap in time periods. Maybe they are in different rooms and so on. And you've decided, at least as a strategy, you want to see as many events as possible. And when you attend an event, you want to make sure you attend the entire event. So no cutting out early so you can catch the beginning of a new event. If you want to go to that new event, you want to see the whole thing and you don't want to have to duck out of any events early. That's just going to make things a little bit easier on us, the algorithm side. And then the goal then is just to take the schedule of all the events, at least the ones that you wish to attend, and try and figure out which events you should attend so that you can maximize the number of events that you attend. So again, this is the real world problem. You can imagine actually encountering this in the real world or having this problem stated to you by your boss or supervisor who wants you to solve this algorithmically. And then it's your job to come up with the formal expression of it, the input and the output. So what is the input that we're likely to get in this case? Now the input in this case has something to do with the events, in particular, the different panels, talks, and so on. What is it about the events that we need to know? We might want to have some label to keep track of them, but it's really their start and end times that are the important parts of each event, and that's what we want to. So we want to abstract away the other stuff, and we only want to keep the stuff important to the problem solving. In this case, it's the start and the finish times, so we will include that in our input. Now, what is the output? Well, the output is some selection of these events. So we want to be able to select events. And in the past, we've been doing this with a subset. We can either directly call a subset or even an index set in some cases where we take a subset of the indexes into the jobs, in this case, events that we might want to select. And then, as we've seen with other optimization problems, that particular set of events that we want to select, there are certain criterias that we want to have be true about that particular set of events. Usually these are criteria that determine whether it would be an acceptable output and whether it would be an optimal output. So in this case, what are those criteria? Well, the criteria I think that leaps out at us has to do with this overlapping time periods. The events that we pick cannot overlap. That's where we get this non-overlapping intervals sort of name here, okay? We don't want them to overlap, okay? And then the other criteria is that we want to have as many as possible, maximize the number of events we can attend. So I'm going to put that together here. I'll formalize that a little bit. Now you'll notice for my input, I do indeed have the S's and the F, the start and the finish time, the start and finish time of our events. I'm assuming we have N events here. And then the way I've chosen to formalize them, there's more than one way that you could formalize this. In the past, we may have done maybe separate lists, an S and an F. But here I really want to emphasize that the start and the finish time are paired together. This is a start time and a finish time for a specific event. Which event? We'll say maybe event I. And so I'm going to put them together as pairs in this set C. Okay, now again, this is only one way to formalize it. You could formalize it another way and be completely successful in solving the problem with a different formalization. The only real criteria is that you have some formalization that is accurate. This one's accurate, so it should be good enough to go. If you don't like it, you don't like the set theory, you don't like the pairing, whatever it is you don't like, that's fine. You could come up with a list-based version and it would probably work as well. Okay, now let's look at the output criteria here. As I mentioned, there's usually two different components here. There's the M, this is the maximum. How many can we pick? And then there's this A. I even mentioned this earlier. Maybe it would be a subset of C. I've explicitly said that here. A is a subset of C. And there's a relationship between the two that I capture here that says the size of A should be M. That is, the subset of events that we pick should be the maximum number of events. So it should be the same size as M. And then all the rest that I have here is just some criteria trying to capture this business about non-overlapping, which is if I have some event C that's in my set A and some other event, Ci and Cj, two different events, Ci and Cj, that are in A, remember A being the set that we're going to attend, then either I finishes before J starts or J finishes before S starts. And that's all that we need. These two here capture the idea of non-overlapping in a formal way, saying if one job finishes before the other starts, or one event finishes before the other starts, then they don't overlap. And that's the criteria there. Now we've just sort of mentioned this, but now I want to explicitly see if we can pick them out. One of these criteria is a criteria of validity. The other is the criteria of optimality. Which is which? Well, what makes our output valid, acceptable, is that they're non-overlapping. If we picked jobs that overlapped, then that wouldn't even be an acceptable solution. We can't be in two places at once. So our condition of validity is, do they overlap or not? Our condition of optimality is that we manage to find the maximum number of such events. So our solution will be valid if all of our events don't overlap with one another. And then our solution will be, again, optimal if we maximize the number of events. So this problem, we could call it conference events, as I've sort of called it here. But this is actually, if we abstract away the fact that we're at a conference and that these are events, these could be, I keep slipping into the jargon of jobs. Maybe these are jobs we want to perform. That's another version of this same problem. And when we abstract away those details that don't really matter, we might just say there's some intervals, time intervals, start and finish, and we just don't want them to be overlapping. And that's how you might find this problem online if you do a quick search for non-overlapping intervals. All right, now I've actually selected this problem because there are a number of greedy algorithms that jump out at us right away that we might want to try. And the interesting and cool thing about them is that most of them seem like they might be correct on first glance, at least. And some of them maybe after a second or two of thought we might say, okay, actually that probably wouldn't work. But at least at first glance they seem adequate. Okay, and this is not true of some of the other greedy algorithms we've looked at so far. Some of the ones that didn't work were kind of obviously bad choices, maybe up front, that we might not have even tried them. In this case, we might have tried them. So let's just take a look at some of them. So I've stated this here, say, maybe Alice and Bob have got together on behalf of us and brainstormed a few greedy algorithms that might solve our problem for us, but they don't know which ones, if any, are correct. It turns out they all might kind of appear correct, but some might be wrong. So let's see which ones we think might be right off. Again, without a proof, without really investigating, just at first glance, which ones might we think are correct. Well, the first one here says, always select the one that starts as early as possible. And that maybe kind of makes sense. If we want to see as many events as possible, we probably want to start as soon as we can. This other one has a similar idea behind it, but it's saying always select the event that finishes as soon as possible. And there's obviously going to be a relationship between these two. Problems or our events need to start before they finish. So maybe the one that starts as early as possible is the one that finishes as early as possible. These might be the same job, in which case, in some cases, these might even be the same algorithm. Okay, but not in all cases, not necessarily in all cases. Okay, now I will say that for both of these algorithms, there are what we might call sort of symmetric algorithms if we started at the other end. So this one says, well, pick the earliest start time. We could imagine, say, the latest start time or the latest finish time. So starting at the other end, the latest ones, and working our way backwards, we could get new algorithms. I haven't included them here because they are technically symmetric algorithms, meaning if this one is correct, the earliest start time is correct, then the latest finish time would also be correct. So these are each paired up with a symmetric other one that would also be correct. Why? Because we can just turn all the input around, make all the start times finish times, and make time run backwards, and then we would run the algorithm and we would get the same result. Okay, well, let's look at some of the other ones here. The next one might make sense. If we are always selecting short events, then we might end up with the most events that we can get by picking as many short ones as possible. So that one might work. And then another one that maybe makes sense is always select the event that has the fewest number of conflicts, meaning that it overlaps with the fewest number of other events. If it overlaps with very few events, then that means it might, it's not going to eliminate many other choices when we select it. So that leaves us the most number of choices to choose from afterwards. Now, all of these, again, at first glance, could be correct. And if you want, maybe just take a second for yourself and think, which ones do I suspect are correct? Are any of them even correct? And maybe I'll just plant a few hints. Only one of these algorithms is correct. The rest are actually incorrect. Now, when we are faced with this puzzle, when we're in college or university, often our professor will give us an answer and say, hey, this is correct, prove it correct, or this is incorrect, show that it is incorrect. But in the wild, in the real world, you usually don't know ahead of time if it's correct or not. And so you don't know whether you should try and prove it correct or you should try and find a counterexample. And so usually the best strategy is to try and do both at the same time. While one of those paths is guaranteed to work and the other one is guaranteed to be frustrating and not work. So you're definitely going to get a little frustration in there, but the goal is hopefully you will find the one that's correct before you get too frustrated with the one that is incorrect. Now, for these ones, again, I already know which ones are correct, which ones are not, but I think what would be worthwhile doing is spending a little bit of time trying to show that these are incorrect, and then if we ever get stumped on any of them that are incorrect, maybe they're actually correct, and so we should try and prove them correct. So let's start here. I'm going to have our 4 different problems here, and I'm going to try and come up with some counterexamples to show that they will not work. So the first one here, the first algorithm that we're going to look at says always select the event with the earliest start time. Now, the way to come up with a counterexample for this is, first of all, when we start thinking about counterexamples, you usually want your counterexample to be as simple as possible. It's true you could get a very complex counterexample to this, but if you can get a simpler one, it's going to be easier for your audience to follow what you're trying to argue, and then it's also just easier to come up with. So in this case, the easiest or the smallest or simplest counterexamples to come up with will be ones with a small number of events. And probably, usually small number of events, what are we talking about? 0, 1, 2, 3, something like that. And usually the first couple are so simple that our algorithm probably works. If we have 0 events, then our algorithm works by default. If we only have 1 event, again, our algorithm already works by default. Likewise, if we have 2 events, it's maybe a little bit harder to see, but I'll let you go explore it a bit. If there's 2 events, our algorithm, no matter what, is always going to be correct. And then it's really when we get into about 3 events where we can start getting into a realm where our algorithm might be doing different things. Okay. Now, why is it? Let's explore that a little bit more. Why would 3 events be important? Well, if you have 3 events, then one algorithm might select one event and eliminate the possibility to select the other 2, while the other 2 could be selected together in a pair, and that would be optimal. And that's exactly the idea that we want to get behind here. So let's see if we can wrap our mind behind that and come up with a good counterexample. We want the event with the earliest start time that if we select it, it eliminates the possibility of selecting the other 2. But we want the other 2 to be compatible with one another. So to do that, I'm going to make the one with the earliest start time be just really, really long. Take a long time. And then the other 2, I can do both of them during that duration. So I'm going to get something that looks maybe a little bit like this. The long one, its start and finish time, take up the whole day, maybe. It's 8 hours long. And we could attend 2 4-hour events, which would maximize the number of events we could attend. So in this case, this is a counterexample. Our algorithm, the one that selects the earliest start time, will select the top job. It will only have one event, and we can see that optimally we can get 2. All right, can we do the same thing if we switch the algorithm from the earliest start time, that's this one, to the earliest finish time? In fact, if we just try and apply it to this job, the one with the earliest finish time is this one, and selecting it is correct, at least for this one. And in fact, this algorithm is the correct one. So I'm going to not try and spend too much time on this. We looked at one, it didn't work. That's usually not good enough, but I know it's correct, and I know we're gonna be frustrated if we keep trying to come up with a counterexample for this one. You can try a little longer if you like, but again, keep in mind you will be frustrated because you won't be able to come up with a counterexample. So pushing along, let's try another one here. Okay, always select the event with the shortest duration. And I want us to be inspired in the same way we were above. We want the one with the short duration to overlap with the other two, just like this long one here overlaps with the other two. But it eliminates the chance of us taking the other two, but the other two are the ones we should take. So actually the idea here that I'm going to do is just shorten this long one down as short as we can make it so that it still overlaps with the two other ones. So, okay, maybe it's not as short as I can make it, but it is still pretty short. The shorter one overlaps with these two, and it would have been better to take the long ones because they were compatible with one another. So again, this counts as a counterexample showing no, the shortest duration doesn't always work. Okay. Now, saying this, I should be clear again, doesn't always work. That doesn't mean it doesn't work sometimes. It might work sometimes. In fact, it might work a lot of the times. It might even work on the convention or conference that you're going to, but it won't work every time because it wouldn't work on this example. And then there's probably other examples that it won't work on as well. Once you find one it won't work on, usually that means there are others it won't work on as well. All right, let's look at this other one here. This one is actually a great example because it's a more complicated algorithm. And I think I've mentioned this previously in previous videos that when you have a more complicated algorithm, coming up with a counterexample or proof is more complicated, okay, or proof of correctness. And in this case, we've got a more complicated algorithm. It's indeed incorrect. And we need to come up with a more complicated counterexample to prove that it is incorrect. Now, I want to be inspired by the same kind of strategy as before. So I'm going to show you how I kind of came up with this counterexample without just showing you the whole counterexample right away. Okay, now, is this going to be, again, the simplest or smallest counterexample? I think it's among the simplest or smallest counterexamples that would work, but it might not be. And if you can think up a cleverer one, please let me know, and maybe I'll update this video and include it. Okay, now in this case, the way I'm going to get started is with the same inspiration. I'm going to have one job, the short job here, that I want to have the least conflicts. It doesn't at the moment, just to double check. I want it to have the least conflicts, and I want to select it like we've done above. And then I want it to, when it does, it will eliminate the chance of selecting these two, and these two should be correct. Now, if this top job did have the least conflicts, then this would be a great counterexample. But as we can see, it has two conflicts. It conflicts with both by design, and each of them only conflict with one. So my first problem is this doesn't work. I don't think I can make it work with 3 like I did with these two. I probably need more events. And my first problem is I need these 2 on the outside to conflict more. They need to conflict more than this guy. So this event conflicts with 2, and I want these 2 events to conflict with more than 2. So they already both conflict with 1. So what I'm going to do is I'm going to add some extra ones on there. Okay. So now, how many extra ones? I just put 3 on each one for now. But now we can see the ones that conflict the most are these 2 in the middle. Okay. Why? Let's just make sure. These ones on the left, these extra ones we add, let's just look at the bottom one, and it conflicts with 1, 2, 3. Our middle one still conflicts with 2, but these ones now conflict with 1, 2, 3, 4. So they actually conflict with the most now. Okay, now that's important. We'll see why in a second. But the problem with this is still not complete. The optimal solution is to select this one and 2 from our other groups. And that means selecting the one with the least conflict. So the least conflict still looks like it's working. Now, this is a good point where I might mention that if you're trying to come up with a counterexample and you're getting this complicated and you're still not being able to, you might be thinking to yourself, hey, maybe I found an algorithm that's actually correct. And this might be a good point to stop and go and try and prove it's correct. However, this one is still incorrect. So I want, in that case, it would be wrong to go that direction. But indeed, it is correct. It is incorrect. So we should be able to come up with a counterexample. The problem is here that the optimal solution, when we were designing it earlier, like above, we're supposed to select these 2 in the optimal solution. Right? So I'm going to do that by adding 2 more jobs, one here and one here. Now our optimal solution, quite obviously, is these 4 jobs. So hopefully that's clear. Now let's see what happens when we apply our least conflicts algorithm here. So least conflicts by design, let's make sure this one was intended to be the least conflicts and it's got 1, 2. This one has 1, 2, 3, so more. Same thing over on this one since it's symmetric. And we already determined that these 2 in the middle have 4. These guys have 4, these ones have 4. So yeah, this is the best one. Okay, so once we've selected it, it eliminates these 2. And we're left now with the option of only selecting one out of this batch or one out of this batch. And I'm going to do that, or we can obviously select one out of each batch. So that will render us with just 3 events that we can attend. When again, we can see quite clearly the optimal is 4. So, okay, let's take a big picture here again. What have we done? We've looked at our 4 algorithms. We've managed to come up with counterexamples for 3 of them, meaning 3 of them are wrong. So we should just push them off the table. They're no longer candidates, and focus in on our 1. The earliest finish time, and try and prove that it is correct. And we are going to try and prove it correct. And as we've done in the previous video, a picture might be helpful. I've used pictures here for my counterexamples, for instance. A picture is going to be helpful for us in our proof, but remember, we want our picture to be as general as possible. We don't want to give up the generality of our proof by making an assumption about our input. So let's see if we can tackle a proof. And as we've done in the last couple of videos, I'm going to do it in 2 forms. One is the sort of fully polished final version that you might find online. And then the second one will be with some extra added details, fill in a few of the added details that make it a little bit easier for us to follow if you're still a student and you're trying to come up with these skills or still build up your skills. All right, so to begin our first proof, let's take a look at the theorem. The theorem that I have here says, always selecting the non-overlapping event with the earliest finish time, that was our algorithm, will result in the maximum set of non-overlapping events. And that was the criteria of the output for our problem. So we can start here with our proof by setting it up by considering the job that we would select. The job that we would select is the event that we would select is the event with the earliest finish time. And I'm going to give it a name, E, so I can talk about it. And I've actually started drawing my picture. At this point in the proof, usually this is a picture that we keep in our head, but if you were, say, presenting this proof to someone, you might actually draw the picture. And so in this case, we've got this earliest finish time, or this job with the earliest finish time, we're going to call it E. And then I also want to consider a set, an optimal solution is what I want to consider here. So I'm going to consider any maximum size set of non-overlapping events. And I'm going to give it a name too. I'm going to call it O. So here I've drawn a candidate O. And there's actually 2 possibilities for O. The first one I'm going to skip over here, but the first one is not as important, so we get rid of it pretty quickly, which is if E, the job we are considering, was already a part of O, then we know that selecting E is optimal and we're done. So usually the way the proofs proceed here is I've kind of made that statement here, is if E is in O, then we know selecting E is optimal, but some proofs will just leave that out. Because it's considered to be kind of obvious or trivial by those who have written a large number of these proofs, but we may not be in that group yet. So I want to keep it in there saying, look, if E is an O, we know selecting E is optimal, and that usually means we're done. That's all we were trying to prove. So let's instead consider, and this is where we go next, is let's consider that E is not an O. So the way I've drawn my picture down here is for the rest of the proof, saying, let's imagine E is not an O, so here's O. Instead, O has some other job. What do I mean by instead? Well, remember, E was the job with the earliest finish time. So let's look inside O for the job inside O that has the earliest finish time. And we've made the assumption that it's not E, so E's out here. So it has to have some other job. Now let's think about these two jobs. I'm going to call this other job E prime so I can talk about it. Now, since E prime is the job in O with earliest finish time, but E is the job in the whole set of all jobs, or all events, that has the earliest finish time, we know that E must finish before E prime. Or as my little parenthetical statement says here, or it could be at the same time. But the way I've drawn my picture is to show that no, E prime comes later, just to make it clear that it could be at the same time, but it could be later as well. Okay. Now, here's how the proof is going to continue. And a lot of our proofs of correctness at this point continue in this way, where we imagine doing a change, a surgery to O. To change it, we're going to rip out the job we don't like and put in the job we do like. So I'm going to say, well, first of all, I'm going to argue that I can do this. It says every job in O, these are all the blue jobs here, other than E prime, starts after E prime finishes. Why do we know that? We know that because O is a maximum size set of non-overlapping events. So all these other events over here must not overlap with this event, which means they must all finish after E prime. There's another important fact here that is sort of being left underneath the surface, which is that we also know none of these overlap with each other because O is optimal. So we don't have to worry about them overlapping with each other. We only have to worry about them overlapping with E prime. Now what we're going to do here is we're going to remove E prime and we're going to put E into O. Okay, so that's what my little argument says here. Remove E prime from O and add in E to get O prime. I've changed it, gave it its new name O prime. Okay, and O prime is still optimal. Now how do we know O prime is still optimal? Well, the reason I made this statement above here is to say that since they all finish after E, none of them overlap with E. They didn't overlap with E prime, they also don't overlap with E, meaning it's still valid. Remember, this was our condition of validity. Then we went ahead and what did we do to make this? We went and we removed one event and we added one E. So the number of events in O prime is exactly the same as the number of events in O. So it must still be optimal. We're seeing the same number of events. But what is the conclusion we can now arise at after we've done this surgery? Is now E is part of an optimal set. Remember above we said if E was already part of the optimal set, we're done. Down below we said, look, it must still be the part of an optimal set. If it wasn't part of the one we picked, it's part of another one that is also optimal. And we're done. That completes this proof. Now, it seems like we only focused on the first job that we pick. That's because the next job is the same choice. After we eliminate this job and all of the jobs that it overlaps with, we can do the same choice for the next job and the next job and the next job. So that's, again, something we leave under the surface. A lot of proofs might leave that under the surface, assuming you, the audience, could fill that in as needed yourself. Maybe you can't. If you can't, then you might want to prove this again with a little bit more detail. So here we go. Let's tackle it one more time, a little bit more rigorously with more detail. Okay, so first off, let's get ourselves started out a little bit more formally by stating exactly what we're talking about. So let's say we're starting with an arbitrary input. So that would be an arbitrary set of n events, and they have start and finish times. Then I want things to talk about. So one thing I want to talk about is our solution. So I'm going to give it a name P. Okay, so here's P. I've given a picture of P, but let's describe it. P is a set of non-overlapping events. So in the picture that looks true, but I need to state that clearly in English or in natural language as well. So I'm going to say that there's a set of non-overlapping events that's selected by our algorithm. And then what else? I kind of want them in an order that I can handle them, do something with them. I'm going to compare them to other events. So I want them in order of their finish time, because remember, that's the order that we selected them in the ascending order of their finish time. So the first one, P1, is this job, then P2, and so on, up to this one. I'm going to call it PI in a second. And then this last one maybe is PD, the last one. Let's do the same thing for the optimal solution. Let's go ahead and pick an O, an optimal solution. Okay, it's got a bunch of jobs in it too. For a moment, they could be different jobs, but for the moment, let's just assume it's any old optimal one. Okay. And again, I'm also going to put it in ascending order of finish time, sort of like this. Okay. Now, we're going to continue the proof in much the same way that we just did the last proof, but we want to consider whether P and O are the same. If they were already the same, if P was equal to O, we're done, just like we were done earlier in that last one. So usually we make the assumption that they're not the same. That's how I've drawn my picture here. Okay. So the next assumption I'm going to make, or next piece of setup really, is let's say that I is the first place, the first event, such that our two solutions disagree. Okay. So the way I've drawn this, by saying it's the first event, this is something that's actually pretty important. It's saying that all the ones before are the same. That's why the ones I drew in P and the ones I drew in O are all the same over here, whereas the ones over here are maybe not the same. Okay, so this is the first time that they differ. All the other jobs are the same. Okay, and this is going to be the first one where they have different jobs. So what do we know about the two jobs? Remember, we always select the non-overlapping event with earliest finish time. So we know the finish time of our event PI must be before or at the same time as the finish time of OI. Okay, so I've captured that by saying finishes no later than. And so we know that this occurs. Now notice that this relationship is the same relationship we saw between our two jobs in the last proof. So the same ideas, the same logical path we're taking here. We've just formalized it a little bit stronger by giving more names to the things we're talking about, making it clearer to our reader exactly what we're talking about. Now we're going to jump into the argument. Okay, here I've sort of visualized what we want to do next. We want to do our surgery to O to get O prime, and we do that by eliminating OI and moving PI in. Okay, so we removed OI, added PI in, and now we want to make sure, we want to complete this argument. We want to get to the point where we're saying O prime is optimal. But to get there, we need to argue that O prime is still valid and still optimal. Okay, and it's the validity part that gives us a little bit more trouble. Okay, so first of all, we want to argue two things. We want to argue that this new job here doesn't overlap with any of these jobs, and it doesn't overlap with any of these jobs. Okay, the fact that all of these jobs in O are the same as all these jobs in P, and we already knew that PI didn't overlap with them, means it doesn't overlap with these jobs either. Okay, we know that P does not overlap with the events O1 to OI minus 1, since they are the same as P1 to PI minus 1. That's what I just said, okay? And we only select non-overlapping events. We knew that the P1s were non-overlapping. Okay, so made the same argument in the picture as I just made in natural language. Okay, let's continue. Now we want to argue that they don't overlap over here. Remember, since PI finishes before OI, or maybe at the same time, and we already know that OI finished before all of these started, and that they were non-overlapping as a set themselves, means that since PI finishes before OI and OI finishes before any of these start, PI must finish before any of these start. And so again, PI will not overlap with any of these jobs, the jobs that come later. Okay, so what does that mean? That means O prime is still valid. So O prime is valid because no events in the set overlap with one another. Okay, good. Now what was the condition of optimality again? It was the number of jobs. What did we do to O prime, or O to get to O prime? We deleted out OI and we added in PI. So the the size of O and the size of O prime are the same. So nothing has changed. So they must be still optimal. Okay, so we removed one, added one, so they still have M non-overlapping events, so it must still be optimal. All right, now after this part, we have O prime now agrees at point I with us, right? I know I moved PI down there, but we didn't actually remove it from P. We now have an agreement on these two jobs or events. And so, I mean, again, a lot of times this extra little bit is cut off the proof because we assume everyone can add it on, but we usually want to add one extra argument here, which is that, okay, repeating this argument, so let's say we did it again and there was another one that differed, like these two, okay? Well, on the next one, we'll swap them out. And then on the next one, we'll swap them out as well, and so on, down the route, okay? Until we get to the end, and therefore, we'll get to a point where P is equal to some optimal solution, maybe not O, maybe not O prime, maybe O double prime, triple prime, and so on. But whatever it is, at some point, we know that P will be equal to an optimal solution, and therefore P itself is optimal. And that completes our proof for the non-overlapping intervals problem. And again, this is just a couple of proofs to get us warmed up and familiar with these techniques. So thanks a lot for watching, and we'll see you in that next video.